Guys, welcome back to TechDose, and in this video we will look at the earliest and latest rounds where players compete, which is from Leetcode number 1900. A prerequisite before watching this is to watch the Bitmasking video. The link for this will be given in the description below. You can also consider solving the problem painting a grid with 3 different colors, which is from Leetcode number 1931. This link will also be present in the description below. This topic is based on dynamic programming plus bitmasking. So 1931 is very similar to this current problem 1900. Let's now read the problem statement. There is a tournament where n players are participating. The players are standing in a single row and are numbered from 1 to n based on their initial standing position. Player 1 is the first player in the row, player 2 is the second player in the row, and so on. So the nth player will be the last player. The tournament consists of multiple rounds starting from now round number 1. In each round, the ith player from the front of the row competes against the ith player from the end of the row. Okay, ith from the front competes with the ith from the end, and the winner advances to the next round. When the number of players is odd for the current round, then the player in the middle automatically advances to the next round. For example, if you have the players 1, 2, 4, 6, 7, player 1 will compete against player 7, player 2 will compete against player 6, and 4 being in the middle, since you have odd number of items, it cannot compete with anyone else and therefore it gets a pass. Okay, so that is the meaning of it. So you can assume that in the middle there is a mirror placed, and if there is a mirror, then if you have odd number of items, then it will go right past the mid item, and so the mid item will get a pass. Whereas if you have an even number of items, like let's assume that you have 6 number of items here, then the mirror will pass right between the 2 middle items, and so the pairing will all be possible and there will be no passes allowed. Okay, after each round is over, the winners are lined back up in the row based on the original ordering assigned to them initially in ascending order. So this is important. The players numbered first player and second player are the best in the tournament, and they can win against any other player before they compete against each other. If any 2 other players compete against each other, either of them might win, and thus you may choose the outcome of this round. Given the integers n, first player, second player, return an integer array containing 2 values, the earliest possible round number and the latest possible round number in which these 2 players will compete against each other respectively. So this problem statement is long, but it is simple to understand, I suppose. Let's look at the first example. In this case, we are given 11 players, which is already mentioned here, and the first player is 2, the second player is 4. So that means the question is asking about find the earliest possible round number in which 2 versus 4 will happen. And when will 2 versus 4 happen? When you have a certain set of items such that 2 and 4 are at their mirror positions when you calculate from the middle. Okay, so we want to find the earliest possible time when this configuration can be produced, and also the latest possible round number in which the same configuration, the similar type of configuration where 2 and 4 are at their mirror positions can be produced. If you look here, then 1 will compete against 11, and so if they are neither belonging to player 1 or player 2, it was also mentioned that anyone can win. So we have 2 choices. When it comes to having a PvP, that means a player versus player, which is not a part of the first player or the second player, then anyone can win. So we have to try 2 possibilities out. In this case, for 1 versus 11, either 1 can win or 11 can win. Okay, so each matchup will have 2 possibilities. So here in the first round, let's say in this example, they have made 11 win, so 11 is retained. If you do 2 against 10, now in this case, since 2 is one of the first or the second player, it is a first player, right? So 2 has to win. In that case, you will just have one choice. So 2 has to win. Okay, and 10 will be gone. Now 3 versus 9. In this case, anyone can win. They have made 3 win for this simulation. Then 4 versus 8. 4 has to win because it belongs to the second player, right? So 4 has won. 5 versus 7. Anyone can win. They have made 5 win. And 6 will not be fighting anybody because you have odd number of items and the mirror is going through the 6. So this is the configuration after one try, and you will see that when 1 won against 11, then 11 came at the end, not in the beginning, because they had mentioned that it will be present in ascending order arrangement. Okay, so 11, since it was already present at the end, it will remain to be present at the end. It will not occupy the first location, right? Now in the second round, when you again apply the same operations, you have 2, 3, 4, 5, 6, 11, and you have 6 number of items, so the middle mirror will go through the 2 midpoints. So in this case there will be no pass. And now if you compare 2 with 11, I mean, what are the players? The first player is 2 and the second player is 4, so 2 with 11, 2 will always win. Okay, 3 with 6, anyone can win. So in this case they have made 3 win, so let's make 3 win. 4 with 5, 4 has to win. Okay, and in this case the first player is 2, second player is 4. Again, if you do the next round, which is the third round, then 2 will compete against 4. So this is the type of configuration that I wanted, where 2, that means the first player is present on the left half, second player is present on the right half, and they are at equal distance when it comes to calculate from the mirror, that means the midpoint. Okay, they are at equal distance, then only they can actually compete. Okay, so that is how 3 rounds were taken, and 3 is the minimum round. If you again play it according to how they have mentioned the second time, then it took 4 rounds to make 2 compete with 4, and because the configuration will change depending on if 2 players are fighting whom you are making win, right? So in this case they have made 1 win, in the previous case they had made 11 win, right? They have made 1 win here. So based on that, you will get different type of possibilities and configuration. And the question was asking about find the least number of rounds in which P1 versus P2 will happen, and the maximum number of rounds in which P1 versus P2 will happen. Just compute that and return the minimum comma maximum in terms of a pair, right? So you can imagine that each pair up, that means each matchup will have 2 choices, and for n items you can have n number of matchups or n by 2 number of matchups, and you can say that you will have 2 to the power n number of possibilities approximately. The n value is 28, and 2 to the power 28 will be somewhat a little bit higher than 10 to the power of 8. Okay, so if you try out all the possibilities, then it may not pass, but I have tried out in this problem, it has passed, because many of the cases will not run when you see the recursion code. But first we need to solve this by recursion. Okay, the first player will always be less than the second player. This means that P1 has to be on the left hand side of the midpoint and P2 will be on the right side. I hope the problem statement is clear. So let's look at some observations. In this case, the gameplay happens by folding from the middle, making the right half come on top of the left half. So if you imagine how the fighting is happening, you can imagine a mirror line right in the midpoint, and so you can fold the paper from one end to the other. We will always be folding from right to the left, let's say, and then you will find the matchups. Or you can move 2 pointers, one from the first point to the one from the other point, and you move L towards the right hand side and R towards the left hand side with equal speed, and you will start finding the matchups. Okay, so in this case, if you make 7, 2, 3 win and 4 gets a pass, then you will have this configuration. Okay, because 7 is to the right hand side, so when 7 wins against 1, it will remain at the right hand side. It has to be in ascending order, right? In this configuration, if again 2 and 3 wins, then 2 versus 3 will happen in round number 3. So it took 3 rounds. Okay, so you can fill this up. 1 versus 7 had happened, then you can say 2 versus 6 had happened, 3 versus 5 had happened in round number 1. And for this example, I had assumed n equals to 7. Player 1 was 2 and player 2 was 3. Okay, so this configuration took 3 rounds. But is this the only configuration? This may not be the only configuration. So we need to explore all possible matchups to get the earliest and the latest rounds for P1 to face off with P2. Now in this case, what we could have done is, again, when 7 was facing off against 1, then anyone could have won, whether 1 will win or 7 will win. When 2 was facing against 6, there was no option, 2 had to win. When 3 was facing against 5, there was no option because these belongs to player 1 and player 2, right? So 3 facing off against 5, 3 had to win. Okay, and 4 will not be facing off against anyone, it is in the midpoint. Okay, so it will be retained. So following the two configurations, you will be getting two different configurations in round 2. If you follow the left side, then 2 will face off against 3, and this happens in round 2. And if you look at the right hand side configuration, 2 will face off against 7, 3 will face off against 4, and again 2 3 will be the one remaining for round number 3, and in round 3 only 2 will face off against 3. For this particular example, these are the only two possible paths which can be present, and therefore the earliest can be given as 2 rounds and the latest can be given as 3 rounds. So you can return the answer as 2, 3 in this particular problem. Okay, so I hope you have got an idea about how we will be trying to solve it. Now in order to solve it, whenever a matchup happens, how will you maintain the reduced number of players? Like how will you maintain the players who are still active and playing and the players who are defeated? In order to do that, you can take an array or a bit set, but a bit mask will be much better, because if you look at the constraint, they have just mentioned about 28 players, and if you take a 32-bit integer, then you have 32 bits, right? So with the 28 players, you can have 2 to the power 28 configuration in the maximum case, and with a simple integer you can have 2 to the power of 32 configurations. With a signed integer you can have 2 to the power 31 configurations. So it perfectly fits inside the integer range. So I will be using a mask which is very simple to operate with, and it is also very fast because bit operations are always faster. Let's say that in round number 1, player 1 here was equals to 1 and player 2 was 4, as I have changed the color. Everyone was active and playing, nobody was defeated. Now if the matchup happens 1 versus 6, then you know that 1 has to win. So what I will do is, I will keep the mask value of 1, that means it is still active and playing in round number 2 when I change the state. But for this 6, since it got defeated, the state will change to 0. Again, when I do the matchup for 2 with 5, I can choose whether 2 wins or 5 wins. Okay, because they both are active. And if they both are active, then let's say that 5 won, then 5 state will remain as 1 and 2 got defeated, so its state will change to 0. Again, when 3 versus 4 happens, then 4 has to win, so its state will remain as 1, but the state of 3 will change to 0. So this is the state in round number 2. Okay, how can you make these matchups happen? You can make this happen by using simple 2 pointers. Okay, you can use simple 2 pointers to make the matchup, left and right pointer. So you move left to the right and right to the left, and you will find the matchups. Now let's say you have this configuration. Okay, now in round number 2, will you actually make 1 fight with 6? Well, that will not happen because 6 is already defeated. So when we take a left and right pointer in this case, then we will see whether left and right can actually fight. They can fight only when they both are playing. That means they both have state 1. Okay, so if you check the mask value here, it is 1 and here it is 0. That means they are not playing. So the right pointer had to shift to the left hand side. It will shift 1 time to 5. Again, in the next recursion call, the 5 state is 1 and 1 state is also 1. Then only they can fight. So 1 versus 5 will happen. Okay, and anyone can win. Let's say that 1 has won, so its state will remain as 1 and 5 state will change here to 0. And then when a matchup had happened, L will increase by 1, R will decrease by 1. L plus 1 and R minus 1. Now you check, can 2 and 4 fight? No, because 2 is actually having state 0. It cannot fight. So L will increase. Can 3 fight with 4? No, 3 is not active. So L will increase. Now L and R being present at the same point means that the same player cannot fight with itself, and this case will happen for odd number of active players. And if this happens, then you will give it a pass and you will break this round. You will go to the next round. Okay, when you go to the next round, again you just have 2 players, 1 and 4, but the L and R pointers will start from the extreme point. Can 1 fight against 6? No. Can it fight against 5? No. Can it fight against 4? Yes. But this 1 and 4 are P1 and P2, and so it happened in round number 3. And so you will break your recursion there. You will have to backtrack and try some other configuration. What some other configuration? when you had actually made this 2 and 5 fight. Here I had made 5 win. Now you can make 2 win and see what happens. Okay, so this is how the bit masking will be applied with recursion. Now let me take an example and show you the recursion tree diagram. I think that will make a lot of sense. So in this case I have 6 players and player 1 is 1 and player 2 is 4. Now in the recursion tree I will be taking the L and R pointer. So the L is starting at 0, okay, and the R is starting at 5. L will move to the right hand side, right will move to the left hand side. Okay, we have the earliest value assigned to you can say infinity, because I want to decrease this value, and the latest value defined to minus infinity because I want to increase this value. You can just take 0 for it, right? Let's start. So initially I will have 1 versus 6. And what is my L and R value? L and R value are 0, 5. Okay, so I'm just writing 0, 5 to denote the index of it, and 1 versus 6 is happening. Now in this case, who can win? Actually, there should have been 2 possibilities, that either 1 wins or 6 wins, but this 6 win condition is never going to happen because 1 belongs to P1. P1 is 1 and P2 is 4, right? So if any one of the P1, P2 happens, then that person has to win. Otherwise, how it will go to the last round? So this 6 flow will not happen. This recursion will be trimmed and 1 will be winning. Okay, so if 1 is winning, then in the next round, what is going to happen? The state will keep changing. Okay, so we have to see the state changes. The state will be changed here to 0, and then when the fight happened, then L will go to the next value and R will be decreasing. That means L plus 1 and R minus 1. So now at this point 2 will be facing off against 5. So 2 versus 5 is happening, and the L value is 1 and the R value is 4. So when 2 versus 5 happens, then they do not belong to any one of the P1 and P2, and they both can fight. So anyone can win. So here you will technically say that, okay, I have 2 choices, and yes, you will have 2 choices for this case. Either 2 will win or 5 will win. Let's say that 2 wins, and let's follow the state. So if 2 wins, its state will be 1 and the 5 state will be 0, and then you will be moving both of them. L will go to L plus 1, R will go to R minus 1. And so your next matchup is 3 versus 4. 3 versus 4. Okay, and the L and R value are 2, 3. Why I am tracking L and R value? Because I will know where the recursion has to break. That means where the round will break. When you reach to the midpoint, when you cross the midpoint or reach to the midpoint, then your round will break. So in this case 3 versus 4 will happen. You know that again you will have 2 choices, whether 3 wins or whether 4 wins, but 4 will always win here. 3 will never win because 4 is belonging to player 2. It is player 2 itself, right? So 3 will never win. This case is not going to work. Okay. So when this happens, then you will see that L goes to the index 3 and R goes to index 2. So L is greater than R. So in this case, whenever that happens, then a new round will start. Okay, so I'm just writing NR here, like let's say new round number 1, new round will start. This is round number 1. In this case, when you check with 3 and 4, 4 has won and 3 actually lost. So this is the state which will be going to the second round, isn't it? So let's say this was round number 1 and now the second round is going to start. Now from here, when the second round will start, again the L and R value will be reset. So where will N and R go? L will be going to this 0. So I will start L here. L will be going to 0. R will be going to the last index. Okay. And again, we can go and compare this 1 with 6. 1 with 6. Now when 1 with 6 is compared, 1 versus 6 is compared, actually it cannot work because 6 is not active. So it will simply be skipped. It will be skipped. And then how to skip? Just decrease the R value. Then 1 versus 5 will be tried. Then what will happen? Again it will be skipped because 5 is also inactive. Then 1 versus 4 will happen. 1 versus 4. And yes, that can work. And if 1 versus 4 happens, then you have already found out that player 1 versus player 2 has happened. 1 versus 4. So this is your endpoint, and when it happened in round number 2. So that means you will be trying to minimize the earliest value and try to maximize the latest value. So both values will be assuming 2, and from here you will be backtracking. Now you can easily track the LR values. This was 0, 5. This was 0, 4, and this was 0 comma 3. And from here you will be backtracking. From 1 comma 5 there is no way that 5 can win. Just one option was there because 5 is inactive. Similarly 6 was defeated and so it is inactive and it will go back. So from this case it will be going back to the previous round. The previous round has 3 versus 4. 3 case was not even possible because 4 was belonging to player 2. So this will also be backtracking. Okay, it will also backtrack to this spot 2 versus 5 in round 1. So let me write it again so that it is easier to understand. It is going to the previous state where 2 versus 5 was happening. And in this case 1 had already won, right? So for this values, let me just write it. 1, 2, 3, 4, 5, 6. Okay, what is the current state? My L value is at 2, my R value is at 5, and the current state of the bit mask is 1 has won, 6 has lost, and rest all states are 1 currently. Okay, and now let's see what happens. In this case, now I will try by making 2 fail, that means lose, and 5 pass. So I will be changing the state of 2 to 0. Okay, change the state of 2 to 0. Keep this as 1, 0, and this is 0, and now 5 has 1. So we will be going to this 3 and R will be going here. That means we will be making 3 versus 4 now. And what is the LR value? 2 comma 3. Okay, index, LR index. Now in 3 versus 4, again there is only one option. 3 winning will not happen because 3 cannot win. 4 is the second player, right? So 3 cannot win. 4 winning will happen. Okay, so when 4 winning will happen, then 4 will win, and this will be set to 0, and again L will go to the right side, R will go to the left side, and this is where we will be stopping. So this is a new round case. Let's call it new round number 2. Okay, I'm just writing a random number. I can write new round dash as well, if it makes sense, new round dash, so that you don't confuse this new round with the previously written new round number 1. They are not related. Okay, now since you have gone to this new round, this is the new state, R2. For the second round, this is the state, and again your LR values will start, and you will have to face off 1 versus 6. 1 versus 6. 1 versus 6 will happen. Okay, now this is not possible because 6 is already defeated. So a right pointer will be skipped to the left and 1 versus 5 will be tried. Can this happen? Yes, it can happen. And in this case, who will win? 1 will be winning. There is no way that 5 will win because 1 is belonging to player number 1. So 1 will be the case only. If 1 wins, then its state will be retained and this 5 state will become 0 and L will increase and R will decrease. Okay, and where will we go? Again, we will have to try to face off 2 versus 4. But 2 is actually defeated. So we will increase this L value and we'll go to 3 versus 4. 3 is also defeated. Then this L and R value are pointing to the same place. Okay, so it will be 4 versus 4. And this is not possible. Actually, L, R value are at the same place. So we have to stop. So in this case, if you have followed the state, this is going to be 0, 0 and this is going to be 1, right? So at the end of round number 2, we have got 1 0 0 1 0 0. That means 1 and 4 are the only remaining states. And therefore, if you follow the recursion tree diagram, it will go to the new round because L is greater than equals to R. If that is the case, then we will be going to the new round. Let's call it new round double dash. Okay. And now again, your pointer will restart from the beginning. And again, you can imagine that I'm just making it in the opposite order, or I should make it somewhere here and R double dash. And then again, if your LR values are at index 0 and 5 with only available state as 1 comma 4, you can imagine what is going to happen. That means if 1 versus 6 is happening, then 6 will be skipped because it is having state 0. Again 5 will be skipped, so 1 versus 5 will be skipped. 1 versus 4, if you do 1 versus 4, then you know that 1 is the first player, 4 is the second player. We are done. The round number is 3. Okay, it is the third round that is running. 2 rounds were done. So now update the earliest value. It will be minimum of 2 comma 3. It will remain as 2. the latest value will be maximum of 2 comma 3, so this will be updated to 3. So what value we will be returning? 2 comma 3. Okay, that is the answer. I hope you have understood the recursion approach and how to manage that. I can say that the time complexity will be approximately 2 to the power of n and space complexity order of n due to the recursion call stack. Now let's look at the code using recursion, and then we will come back and see how to solve this using dynamic programming with bitmasking. Now this is the recursion code, and in this case we are given earliest and latest with n first player and second player. Here I have given a small explanation about how the bitmasking works. You can go through it. I have already explained it. So I have taken a global variable inside the class as n, and I am defining this n, saving it in the global variable so that I will be reusing it in our utility function. The mask value will be 1 left shifted by n times -1. This will create all the set bits, as you must be knowing. The first player and second player will be subtracted by value -1, because even though I have shown you with one value, what I will be actually doing is I will be setting the player numbers as the same as the index are given, so that I will be able to write easier code. It will be simple and readable. Okay, so if everyone is solved based on index starting from 0 to n-1, if p1 is let's say 2 and p2 is let's say 5, then they will also be shifted one time to the left. Okay, so it will become 1 comma 4, and that is what is done here. Then all possible matchups have to be tried using the first player and the second player and starting with the mask. Okay, now 0 and n-1 are actually your left and right pointers, so the left pointer will move to the right and right pointer will move to the left hand side. Okay, now this 1 is actually your round number. Now after processing we will be having the min rounds and max rounds. These are also globally defined inside the class. If you look the definition of the class, you have n, the min rounds and the max rounds. I want to minimize the min rounds, maximize the max rounds, hence the assignments are int max and int min. Now in the recursion, all possible matchups, see we have a mask left right, p1 p2 and the rounds. Left right are your l and r pointers. Now if l is greater than equals to r, then we know that the round is done and we will be going to the next round. When we go to the next round, l will be shifted back to the start point, which is 0. R will be shifted back to the start point from the right hand side, which is n-1. P1 P2 is never going to change, and the round will be incremented by 1 count because we are going to the next round. Otherwise, if L is to the left of R, then we will be checking if the current left hand side player is actually active. Okay, if it is active or inactive. So in this case, if it is inactive, then I will be skipping that player and move to L+1. Okay, otherwise if the right player is inactive, then I will be skipping it and moving to the left to right -1. Okay, all these three base cases are done. Then another case is if L and R are pointing to P1 and P2. If that is the case, then you are done with the round. You have to backtrack now. So you will be taking a note in min rounds and max rounds by minimizing and maximizing whatever rounds you have counted till now. Otherwise, if none of the base cases hits, these all are the base cases. If none of the base cases hit, then in general, I will be checking that left is neither equals to P1 or P2. That means it is just a normal number. Okay, right will definitely exist. Otherwise, if right do not exist, then this case would have hit. Okay, so if left is not equals to P1 and P2, then I will be trying to make right win. And how can you make left lose? When you set its mask value to 0. So if you take XOR with 1, then it will become 0. So set the mask value of the left side item to 0, left side player. So you are making right side win. And you go to left +1 and right -1. That's it. And you try the other possibility where the right hand side is neither player 1 or player 2, then make the right hand side lose. And in that case, make the right hand side mask value set to 0 and move to left +1 and right -1. So this is the simple recursion approach, and I hope it is clear. Once you have understood this, let's now look at the dynamic programming approach. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. Now, in order to understand dynamic programming, we just have to think about what are the repeating subproblems or how to define a subproblem. So in this case, if you have noticed, L and R will be something that you may choose to be defining subproblems, and also the mask, because each of the mask is going to be unique, right? So if you are thinking about taking mask as the state, then definitely it will give you correct result. But the combinations with the bit mask can be 2 to the power of 28, which is around 10 to the power of 8, and even more than that. So if you have 4-byte representation for each mask, because we are going to take integer, it will cost you 1 GB of space approximately, which will give you memory limit exceeded. So you cannot use the mask as your state, even though it will give you correct answer, but you cannot use it. Okay, then this option is gone. The next option was your L and R, right? So what if I track the positions L and R? Will it work? Well, this will not work. I have already given you an example. In this case, if I say that the first one is subproblem 2,5, let me change the color. So the subproblem 2,5, this means that L is at index 2 and R is at index 5. Then this other state will also mean 2,5, but are these subproblems the same? They are not the same, right? These two subproblems are not the same, and therefore two different states can be represented using the same LR value. So how can you say that LR is going to work? It is going to give you wrong answer, because when I define DP states, then I should say that if I have LR as the DP state, then if another LR happens, it should refer to the same solution actually. But if it is referring to two different problems, then definitely two different solutions will exist. So I cannot assume that they are the same subproblem, right? So that is the problem with this option 2. L and R itself cannot be used, the index cannot be used. Okay, now what is the third option? The third option is about counting, because this problem, even though it looks like a simple dynamic programming and bit masking problem, but this is based on some kind of geometry. If you have already figured out, it is based on geometry, that means counting. Because if you want to do a certain matchup on a number line with player 1 and player 2, then you have to identify where is the midpoint and how many active players are in the middle, so that they will be defining what is the distance from the middle for P1 and P2. This is what matters, because let's say that you cannot just say that in between P1 and P2, if there are 4 players, then they are equidistant. Like let's say player 4, 5, 6, 7 are in between, then are they equidistant? Well, that equidistance will depend on how many are active players in the middle. Maybe 4 had won and 5 actually could not win, 6 had won and 7 could not win. Can this configuration happen? Yes, it can happen. And if this configuration happened, then how many are active players between this mirror and P1? 1 active player, and between the mirror and P2, 1 active player. So this will say that if you fold it, then P2 versus P1 will happen. Okay, you could have had 5 items as well, but it depends on the count of items in the middle, which will tell you if the geometry is going to have P1 versus P2. So the middle counter is very important. That's the first thing. Another thing which will shift the position of P1, how far left or right it will be, depends on how many players on the left hand side had won. If more players on the left hand side are winning and to the right hand side of P2 are losing, then you can imagine that this P1 and P2 will be shifting to the right hand side. Okay, so you will have more items on the left and P1, P2 will shift to the right. So the midpoint will come somewhere here. Then how will folding actually make P2 fight with P1? It will not, right? So how many players are on the left, active players on the left, active players on the right, and also the number of players in the middle will define an appropriate configuration and geometry where on folding the P2 versus P1 is going to happen. Figuring this out is difficult, I know, but you are here to learn this. So please make sure that geometry is also one of the topic that has been included in this problem. It is subtle. You will get a hard time understanding this probably. So you can take pen and paper and try to write it out. Okay. So in this case, I will maintain L at position where P1 is present, and I know that P1 will always be present to the left hand side of P2, and R where P2 is present, and L will give me a count of how many active players are there to the left of P1. In this case, L will be equals to 1 because only one is active, only one player, right? And R will be equals to 0 because there are 0 players active on the right hand side for this given state. M will be telling about how many active players are there in between P1 and P2. These three combined together will always define a unique state. If you think about, okay, how it is defining a unique state, like let's say if I had 00 and 11, then how is this state the same as the previous state? Yes, it is the same because it depends on the count. This problem is about geometry. It is not about who fights whom. It is about geometry. Okay, you have to understand that. So whether 4 5 is present in the middle or 6 7 is present or somebody else is present, it does not matter. It does not matter. The count is what matters. Count in all these three regions is what matters, and that will be our state. Okay. So consider making L, R, M as the state. L is the number of active players to the left of P1, R to the right of P2, and M in between P1 and P2. These are all active player count. Okay. So this third option is what we will be seeing. And since you know that the maximum players are N, and if I safely take the number of players, that is N is 28 maximum, then I can take 3 states as N cube, N into N, all possible combination. And for each of the state, I have to parse this entire state from left to right, or you can say using 2 pointer L and R, the left and right pointer as I had shown you, right? To do the matchups as I had shown you in the recursion, same code I will apply. So this entire process of matching up in the round will take order of n time. So an n time will also be multiplied, and therefore the time complexity is going to be order of n to the power of 4. And this is well within our 10 to the power 8 range. Okay. The space complexity will be n cube to maintain all the states of LMR. And I hope this is clear. If this is clear, let's now look at the DP solution. Now in this problem, if you see the earliest and latest, this entire thing is same, except that we are sending 3 extra parameters L, M, R. That means the count of active players on the left side, count of active players in the middle and on the right side. Okay, except that everything else is same. If we move up, then you will see that everything is same except for this LMR addition, and now all the cases are also same, right? How will it be different? It is same. If left is greater than equals to right, then actually we are done with the round, so we will be going to the next round. So we will be resetting L to 0, that means the left to 0, right to n minus 1. Rounds will increase, LMR will remain to be the same because the count will be unaffected with the base cases. LMR will not be affected with the base cases. So for all these cases, you will see LMR will not get affected. I have already explained this, right? So you can go through. If the matchup happens, then minimize the min round, maximize the max round. Otherwise, if you have not seen this state LMR and you are reaching here for the first time, then only I will be calculating it, only the unique sub problems. Mark it as seen, that means true. And then you see that the left hand side, if it is neither equals to P1 not P2, then you can make the right hand side win, that means left hand side lose. And if you are trying to do that, then the mask will change. Left will go to left plus 1, right will go to right minus 1, P1, P2 rounds. And then what happens is, if your left is actually to the left of P1, then if left loses, then the count of this L will decrease by 1. And that is why the update is happening. If this left is actually to the left of this L, that means P1, then the left count will decrease by 1. Otherwise, if this left was not here, but this left was in between P1 and P2, then the count of M will decrease by 1. Otherwise, if this left was somewhere to the right of P2, then the count of R count will decrease by 1. And that is what is updated here. Okay. The same thing goes for the next round as well. If you try to make the right lose, if it is not equals to P1 or P2, then if the right is to the left of P1, then the L count will decrease by 1. If it is in the middle of P1 and P2, M count will decrease by 1. Or if it is on the right hand side of P2, then R count will decrease by 1. That's it. Otherwise, the entire code is same. I hope this solution is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.